Hi there and welcome back to the triplicate digital synthesis tutorial and part 7. Last time we got the envelopes working and we figured out how we were going to set up and modulate the various parameters that control the synthesizer. This time we're going to move on to the filter and button up a couple of other things so we've got a basic functioning synthesizer. The main green we set out to design as a traditional analog type synthesizer, and the main filter is sort of the heart of this kind of synthesizer. So it's worth us taking some time and going into it in some detail. We want to design a resonant low pass filter which can be switched between 12 or 24 dB. This is the most common type used. There are several ways of implementing this, but I am going to tell you about the one I used in the Red Sound, Dark Star and Elevator. And here we have a resonant filter. And yes, it's a piece of elastic and a chunk of metal. Okay, so imagine my hand here is the input to the filter and the position of the chunk of metal is the output. If I move it up and down very slowly, the output follows the input, and if I move it up and down very quickly, the output is still stationary, so it's filtered out the input. And if I move it up and down at a certain frequency, you can see I'm moving my hand at the top here very little, and the piece of metal is bouncing up and down quite a lot. So it's resonant at that point. So let's see what's going on with this and see if we can turn this system into some equations that we can design a filter around. Okay, so here's our system. We have a spring, our elastic in my little demo, driven by a finger, the position of which is X, the input to our filter. We have a mass, which was our chunk of metal in my demo, and we have a damper. This is shown as a piston pushing some fluid, like a car shock absorber. In the demo, our elastic absorbs energy as it flexes and hence provides the damping. Okay, let's consider the force on our mass. We have the force of the spring. K is a constant, depending on how much force it takes to pull the spring a certain distance. And we have the damping, which is proportional to the velocity and always trying to slow the mass down. So we can write the equation for the force, F equals K x minus y minus d, the damping, and according to Newton that is equal to the mass times the acceleration. Now we're not trying to represent any real physical system, so we can set our mass to 1, giving A equals kx minus ky minus dv. Now a bit of maths. Acceleration is the rate of change of velocity, and velocity is the rate of change of position. But since we are sampling, one sample is the smallest unit of time we can consider. So the change of velocity being between one sample and the next is the acceleration times the sample time. Now it turns out we could actually make this change in velocity the acceleration multiplied by a gain factor, and conveniently the cutoff frequency of the filter is then proportional to this gain factor. So here VL is the velocity of the last sample, and we get the velocity of the current sample according to this equation. And similarly for the output Y, we can calculate that from the velocity, like this, and this gives these three equations for our filter. Okay, so now let's test it out. But before we do so, a couple of things to note. The cutoff frequency of the filter is given, as we said, was proportional to the gain, and it's given by the gain times the sample rate over 2 pi. And the resonance of the filter, that's how many times more it is at the resonant point than it is at the low pass, at the low pass point. That's just 1 over the damping. Okay, and for now we're sticking to low pass filters, but it turns out that the velocity v gives a bandpass output and the acceleration a gives a high pass output. I shall return to these at some point. Finally, there's a PDF document with the downloadable files for the wave, the code and the sounds, that gives a lot more of the mathematics if anybody's interested. So here it is, coded. I've created a filter structure for tidiness, but apart from that it's pretty much the three equations we derived just now. Okay, so I've fed this with a sine wave that increases in frequency logarithmically from 10 Hz to 10 kHz. And as you can see here, I've just set the gain to 0.05 and the damping to 0.16 fixed values. And here's the result. As you can see in here, it's doing what we want it to do. For now, I'm using floating point calculations, so now let's implement it in our PC test synthesizer using 32-bit integers, as it will be in the mean green. Now, we developed our filter using floating point arithmetic, and I'd strongly recommend that you do use floating point wherever possible. I'm now going to go into a bit of detail on the filter implementation using integer arithmetic, and I hope this will demonstrate why floating point is much better. The first point to note is that a resonant filter can have gain. In the mean green we're allowing for a resonance of up to 10, and if we have two filters in series to give a 24 dB per octave cutoff filter, this could have a gain of 100. In a 16-bit system where we want the output to fit in 16 bits, we would need to divide the oscillator signal by 100 to stop it overloading the output of the filter. Thus, to achieve this, the oscillator signal going into the filter would have to be 9 bits, or 128 times, lower, which we've already decided, if you look back to the oscillator tutorials, is completely unacceptable. In practice, in 16-bit systems, I'd probably use 12 bits for the oscillator. Since we're not using a sine wave oscillator, so the output of the filter will never be quite 10 times, and if it does clip, it just clips, and we'd have to live with that. However, we have a 32-bit system. This means that we can use 16 bits for the oscillators and still have plenty of headroom for the filter resonance. We only need to drop to 16 bits to output the samples to the D2A at the very end, and we achieve this by allowing the user to turn down the final volume level if the output is overloading. So here it is. The main filter is just a container for the two 12 dB per octave cutoff filters. And we can select one for a 12 dB octave per octave filter, or put both in series for a 24 dB per octave filter. I have some plans for doing more creative things with the two filters, but that'll have to wait for a later tutorial. And here is the 32-bit implementation of the 12 dB per octave filter itself. As you can see, I've replaced the acceleration, velocity and position variables with low, high and bandpass variables, as this is more meaningful in our application. Apart from that, it looks pretty similar to the floating point implementation. That is, apart from, as you'll have noticed, I've implemented the multiplications as a function. The reason I've done this is because of the problem with multiplication in integer systems, especially using the C language. Okay, let's say that we are scaling a floating point signal of 0.7 and we're scaling it by 0.5. This will give an output of 0.35. And now let's say we're using an integer system to represent these numbers, where we are representing the floating point values of 0 to 1.0 by the integers of 0 to 100, i.e. 100 times the floating point values. This makes it easier to describe than giving examples in hex. Okay, in this case the calculation will become 70 times 50 equals 3500. Now the answer we actually want is 35, 100 times 0.35. So here we notice two things. First, we need twice as many digits to store the result of the multiplication. And second, we need to scale the multiplication back down, in this case by 100, to get it in the range we want. In general, if we multiply two 32-bit numbers together, we get a 64-bit number. You can see that for the PC version I've actually cast the inputs to 64-bit numbers before multiplying them. In the ARM processor that the STM32 uses, the 32-bit multiply instruction places the 64-bit result in two registers. The compiler provides a special method to access these. I'll be going into that in more detail in the next mean green build video. Finally, you'll notice here that when I shift the multiplication back down into the 32-bit range, I allow for an additional scaling to be applied if required. Okay, so now we've got our filter. All we need to do is drive it. I haven't implemented all of it, so for now here's what we can do. We can set the configuration to 12 or 24 dB per octave. We can set the cutoff frequency and an amount of cutoff frequency modulation from envelope 2. And we can simply set the resonance to a value. This is the bare minimum we have to implement to make it into a playable synthesizer. The cutoff and resonance values that we set from the controls are turned into gain and damping values, which are used by the filter. To do this, we use interpolation from tables in pretty much the same way as we use for the oscillator. The filter cutoff is set up so that the control knob is setting the pitch of the cutoff frequency. So if the output from the knob increases by 12, the cutoff frequency of the filter will double, i.e. an octave. Now the resonance simply scales the knob value down from 1 to 10 and inverts it to give the damping. And as promised, a very quick look at the mixer. The mixer does two jobs. It mixes between the two oscillators, and this mix will eventually be modulatable. It also applies the main envelope, and eventually the note velocity will be applied here as well. So we have a synthesizer, and here's a little sequence of notes. This is the very basic sequencer format I developed just for testing the PC version. I gave an overview of how it works in a previous video. So for now, let's just run the program and see what we get. Okay, so here it is. Let's run it. And there we go, it's generated our sequence of notes. Let's hear what it sounds like. So there we go, not likely to be taking the clubs by storm, but now at least we have a working synthesizer. So that's it for this synthesizer development tutorial. Next time we're going to look at LFOs and have a more detailed look at modulation. And in the next Mean Green synthesizer hardware development video, I'm going to implement this very basic synthesizer code in the hardware and actually get it to play notes from a keyboard. So just so it feels like it's really moving forward. So, if you like the channel, please subscribe, leave a comment if you've got anything to say on the video, thumbs up would be nice, and I'll see you next time. So for now it's goodbye from Triplicate, home of interesting electronics. Goodbye.